So let's come back to really going through and introducing the process that we're going to be using now for statistical pattern recognition. So we introduced the high-level concept for this right back in week 1, so they had an idea of where we're going. So I just want to recap on this, but then I'll start to turn this into what are the specific probability relationships that we're going to need, and I'm going to lead us through into the use of the Bayesian, the Bayes rule in terms of the way that we're going to work here. So this is a slide that we saw in week 1. It's just a recap from this. We've got 3 stages that we're going to be thinking about in this course in terms of the way that we manage stuff. We've got input patterns that come from the outside world that might be measurements of, if you're doing an image processing, it may be an image that you capture from a camera. If you do sound recognition, the sort of thing that I'm doing, it might be a sequence of sound pressure level values. And these are captured by the sensor, which will then give a series of measurements Y. So Z is our input pattern, Y are our measurements, which is our pattern representation vector. So Y contains everything that the sensor is going to tell us about the pattern that's just come in here. And Y is what we have that we've got to make our decision on the basis of. Then we have a stage of feature selection or feature extraction, which is where we try to reduce the complexity of this Y input into something that's more manageable that we can then give to our pattern classifier. Now, as I think I mentioned, in terms of those of you that are taking courses related to things like deep learning, the feature selection and feature extraction and the classifier are often considered together, where the feature extractor or feature selector is learned as part of the classifier. But for the purposes of this course, we want to consider these as separate processes so that we can see what's going on. So we'll talk later in the course about feature selection and feature extraction, but for this lecture and the next lecture, we'll be focusing on this step, which is the classifier. And often we'll look to see, maybe in our examples, can we get a 2-dimensional, 3-dimensional input for X? So can we reduce the number of features down to something that's manageable or visualizable sometimes if we want to get a pictorial view? So here's an example if we wanted to recognize printed or written letters. We could look to find the center of gravity for this lecture, measure some points out from that center, and here we've got 8 values Y, which gives us a sort of a silhouette for this shape. And an A shape and a B shape would be expected to have different values. Clearly, we haven't captured everything about here. There are holes in the middle that we're not measuring, but this may give us enough as a starting point from here. So that would be our sensor that will give us our input Y. And then we may want to do feature selection or feature extraction to reduce this down to a smaller number of values that we use as the input for our classifier. So a few bits of notation here. Often we'll use M as the number of classes. You don't have to use these numbers, these letters, but many texts will tend to standardize on certain notation, so it's very easy. It makes it easier to read from one paper to another. Omega is typically used to indicate a class. So omega I is the ith class. If we've got 2 classes here, 1 and 2, then omega 1 and omega 2 are the 2 classes that we're talking about. So if you see a pattern recognition problem and people talk about omega, you don't have to explain that omega means the class all the time, because everybody understands in pattern recognition that if you're talking about omega, you normally mean classes for lowercase omega. And then you've got a probability of X given omega I. This is the distribution of patterns. So the density, probability density of the pattern features given that particular class. So suppose that you've got things in this first class, the A letters, you've got lots of different shapes here. You would consider that you've got a probability density of those different shapes in some region of your X space here. Here we're using a bold X to denote that this is a vector. Sometimes you don't always write that. Here we've just got an X written as an italic. If I'm writing on paper, I'll typically use an X underscore for that to indicate a vector. So just if it's not indicated as a vector, normally expect that this is a vector. Then finally, at the far end, you've got some decision, and the decision is which class is this in? Is it class omega 1 or class omega 2? So that's the decision that we need to take. So here we're dealing with probability things. So the class and the pattern vector we think of as random things. They're randomly generated items. It can take a little bit of getting used to the idea of what a random vector or random variable is. So here, a random variable, I'm not going to go into the technical detail. In the supplementary material, there's a long discussion about what random variables are. But essentially, this is something that takes a value. So in this case, our class omega could take the value 1 or 2 for the class that we're or it could take the value omega 1 or omega 2. But the pattern or measurement vector X, it can take different values with different probabilities. So if you like to think of it like this, there is a sort of density that this has. So X exists in certain places, and if I write this something, the probability, joint probability of X and omega, we could think of the probability of X being somewhere in a two-dimensional plane and omega being one of two values. So you could almost think of it as two planes, one on top of the other. There's some certain probability that it will be in the omega 1 plane, certain probability of being in the omega 2 plane, and that sort of joins two different things together that could be happening. One is where is X, and one is what value is omega. And if all of my omega 1s are over here and all of my omega 2s are over here, then you can sort of imagine two different blobs on the two planes. And those will give you this joint distribution. But in many cases, we don't see this joint distribution. We're dealing with conditional distributions a lot. So we can unpack this conditional distribution into joint distributions in two ways. One is the probability of X given omega times P of omega. This one says, suppose we knew which class it was. This is the distribution of our values. So if I go back just a couple of slides to this picture, if I knew I was in class omega 1, I can imagine a sort of probability cloud in this green space. If I knew I was in class omega 2, there's a probability class over here. So this is our probability of X given omega type classes. Oops, let's go back to here again. So that's the one for each class, and then to construct this joint distribution, I then need to multiply that by the probability of the individual class. If they're equal, this is easy, and this is a half, but in many cases they're not equal. But the other way that we can split this joint distribution into conditional distributions and a marginal distribution is to write that P of X and omega is the same as P of omega and X, just with swapping around the variables. And that's P of omega given X times P of X. And this is usually the thing that expresses what we want to know. We're given an observation X, we want to know the probability of omega given that x. But in order to make that into the joint distribution, we have to multiply by p of x here. So both this formula and this formula are alternative ways of writing this.
Is there a way to visualise that p of omega given x in that picture earlier?
Yeah, I've got some one-dimensional visualizations I'll be bringing up in a moment to see that. So this is sometimes known, this p of omega given x is sometimes known as the a posteriori class probability, or the posterior, depending on how your Latin is. And so the idea is that p of omega is the so-called prior probability. If we didn't measure x and we wanted to guess what the classes were, this would be p of omega. It's just how likely the classes are. We haven't measured everything. This is our best guess. But if we measure x, we've now got p of omega given x. Given that measurement, we now have a new distribution over the classes, and this is the posterior. So there's the idea of the before and after, prior and posterior idea of measurements. This one, p of x, that looks a little bit awkward, actually, if we know these p of x given omegas, which are our models, we're going to assume we know these, I'll talk a little bit more about this in a moment, and we know the prior probabilities, then we can just sum all of these up to integrate out the omegas. So, or sum out the omegas. So this will give us our p of x. This is forming the marginal distribution p of x from actually this, which is the joint distribution. So all this is doing is integrating out the omega to form that. So just a little bit about notation. Here I've used an uppercase P where there are probability distributions over things where there are a finite number of choices. So for our classes, omega, we might be choosing two classes, omega 1 and omega 2. But for our lowercase x, for our x is a random variable over a sort of continuous distribution of things. And so for that, I tend to use a lowercase p for that. But some of the textbooks will use lowercase p for both sort. You just need to keep track of which one is which sometimes. So die roll, for example, comes up 1 to 6. You talk of uppercase p for that, of the probability of each item. Whereas the measurement of a height of a person or a position in a room, we'd normally think of a lowercase p for probability density of that. You can't say exactly what's the probability that somebody's height is 1.357 meters, because it may be slightly more than that or slightly less than that. It's more interesting to say what's the probability density around 1.57 meters. Okay, so this is where we then start to turn these probabilities into the decisions that we're going to make. So ultimately, we want to decide something because we're going to have to take an action. So, and actually in any of these probability related things or pattern classification, it's always worth asking yourself, why am I doing this? Why am I sat in this room? Why am I wanting to decide, am I class 1, am I class 2? And that's usually because you're going to take an action. And if you take an action and the decision you made is wrong, there'll be consequences. So there'll be a cost of making a mistake. But usually, a measurement that you make helps you to reduce the cost of mistakes. So if you want to choose which module to take, you'll read the module description on the web, you'll come along to the first couple of weeks lectures, and you'll use that to form an internal probability model which either says which module do you think is going to be most interesting or most useful or going to get me the best marks, and you'll try and maybe balance those things up, but ultimately you have to at some point make a decision. And if that decision is wrong, then might not be so interesting as perhaps another one might be, or you might not get quite such good marks as you might have done on another one that might have been easier or closer to your background. So there is some cost of making something wrong, and that's the thing that you need to keep in mind all the time. Most of the time we'll make some simple assumptions that say, well, let's choose the one that's the highest probability of being the thing that we want. So suppose your idea is you want to get the highest marks. You could estimate how much you think your background is matched to a particular module. You can guess what's the probability of a mark range I might get, and you'll choose the one that gives you the highest estimate there. And if you didn't know anything, then you want to minimize the probability of error just by choosing the most likely class for things. So suppose that we draw a ball from a bag and we want to guess what color it is, but we're not allowed to look at it. We might just guess based on the fact that somebody's already told us that there are more red balls than there are green balls, so we'll just guess it's a red ball. But now, rather than actually being able to look at the color, perhaps somebody rolls some sort of, makes some strange measurement about it. Perhaps you're red-green colorblind, and you just have to make your measurement based on gray level. In that case, you have to guess what the color is. And there'll be a new probability, and that's this one here, the color based on the measurement that you've made. And much of the time you might be right, but sometimes it might be wrong depending on whether you've got a particularly brightly colored green or darkly colored red, or the other way around. So this is this difference between the prior probability and the posterior probability. And on the whole, your error will be lower once you've made that measurement. And so if you're making classification that costs something, this will give you a much better outcome. So medical measurements you might be making, security measurements, these sorts of things will help us. And the use of Bayes' theorem here helps us to find these posterior probabilities by knowing this model probability, the so-called class conditional density function. It's called class conditional because it's probability of X given the class. And this rule that says choose the thing that is the most probable one after we've made the measurement, so using the posteriors, is called the maximum a posteriori. Let me get my teeth around that one. The maximum a posteriori probability rule, or MAP rule. And that says estimate the probabilities of things after you make the measurement and then choose the most probable one. This is the obvious rule that we'll be using a lot of the time. And then here is how you use Bayes' rule to do this. So we can calculate these things as long as we're given certain numbers. So the class conditional probability here, we're going to assume that we're either given this or that we can estimate it. And when we come on to talk about supervised learning, we'll talk about how we'll estimate these for different classes. The prior probabilities, again, we're going to assume that we're given those or that we can estimate them. And if you look into what's sometimes talked about Bayesianism arguments, there are discussions about whether you can really deal with these prior probabilities, whether they really exist or not. But on the whole, we'll tend to estimate how often classes come up and use that as prior probabilities. And then we've got this whole P of X here, the probability of an observation, and we saw a couple of slides back that we can calculate that based on knowing those and integrating out the omegas. And there are a few things that we can use here that help us in terms of the sum over all the classes are going to be 1, because it must be one class that it's come from. This is our assumption that one of the classes it's come from must be true, and that they're mutually exclusive classes. So we're assuming that in the case of, we talked about earlier on, lecturer and student on a class, we're sort of assuming that these classes don't overlap. So you're either a lecturer or a student, you're not both a lecturer and a student in the class at the same time. We also assume that given a particular observation, X, it must have come from one of the classes. So given that we've seen an XY measurement in this room, it's either going to come from a student or a lecturer, and the sum of those probabilities is also going to sum to 1. There's a similar thing from the positions. The integral of the probability density over all the possible positions, X, is also going to integrate to 1. So our measurement must come from somewhere in our measurement space. And the sum of all of those probability densities, or integral in this case, is going to integrate to 1. And the same thing happens with the conditional one. When it's conditioned to come from class 1 or class 2, the integral of all of the measurements given class 1 is also going to integrate up to 1, because from class 1, once you know that, it must come from somewhere, and the total probability of coming from any place is going to be equal to 1. So we talked about trying to visualize some of this earlier, and here's a bit of graphical view to see how we can visualize this. And rather than trying to draw it on two sort of planes, what I've got here is a one-dimensional measurement. So here our X, instead of being a two-dimensional vector or a higher dimensional vector, is just one direction along here. So this is our probability X, and here I've got a blue class and a red class. And here are two probability densities. So these are Gaussian or normal distributions. You can see that they have two different means. So the blue mean is here around 50, the red mean is here around 100. But they also have different variances. So the red class is spread more than the blue class is. And so you can see it has a wider distribution here. Also, another important feature here is there's an overlap between the two classes. So that means that around here we've got 60 to 80. In this region here, if you have a measurement of a vector X, or in this case a single value X, in this range from 60 to 80, there's it could have come from either of the classes very easily. From this diagram, we can't tell exactly which of those is most likely, but we know that you could have a measurement of 60 that comes from the red class, you could have a measurement of 60 that comes from the blue class. Either of those are possible. And this is really where the question for pattern recognition that we're trying to do and why we need to know probabilities comes into this. Because if we ask the question, I've measured a value of 70, what class does that come from? One answer is, well, it could have come from either. Don't know. But at some point, suppose you say, well, I have to make a decision. What decision should I make? Should I say it's more likely to be the blue or the red? Well, let's now work through some probability work to say, well, we're going to have to choose one, so let's choose the one that's going to be the most probable class given the measurement. And let's look graphically what that means. So on our Bayes theorem here, so the version of Bayes that we got, instead of P of x given x given y, we're going to turn this one into the version of Bayes that we want is P of omega I given x is P of x given omega I P of omega I over P of x. And if we want to measure the biggest P of omega I given x, one trick that we can use already is that the P of x's are going to be the same for both sides. So actually all we care about is the top of this part. So let's just work through to see what we end up with for this decision and where it's going to take us. So the first one, P of x given omega I times P of omega I. That's the top part of our Bayes theorem here. Well, here this blue curve and this red curve represent P of x given omega I for the blue curve, and P of omega I is the relative amount of each one. And actually, although this one looks higher than this one because that one's spread more, they're actually about the same area. So it's really the area that's important for that. So we've really got two curves. We've plotted them one on top of the other, but if you like to think of this as really it's two graphs, one with the blue behind, one with the red in front, and we're really just looking through two graphs at the same time. So one of these graphs, P of x given blue, if you like, is this blue curve. The other one, P of x given red, is the red curve. So we've got two graphs here. Then we've got this total density distribution, the one that says, okay, what's the distribution of x from any class? And that's the one that we get if we sum up those two. So we sum up P of x and omega I for omega 1 plus for omega 2. In other words, P of x given omega I times P of omega I over both class 1 and class 2. And this is this total probability density that we get. We can see there's a sort of gap in the middle here. And this is a very common thing that you'll see when you look at classes that come from different places. You'll see a dense bit here and a dense bit here that correspond to the two different things that there are, and a gap in the middle. So if we take this class, there's a dense bit over there where many people are sat. There's a dense bit over here where one person is standing, and there's a gap in the middle where there aren't any people. So even though we don't know the classes yet, we can see that there's a gap in the density. And when we come on to unsupervised classification, this is one of the clues that allows us to separate things even though we're not told what the classes are yet. Yes, question.
So the blue curve and the red curve are the P of x given omega I
Yes.
for I1 and I2.
Yes.
But does that curve tell us anything about P of omega I?
No, it doesn't.
That's information from somewhere else.
So that's information from somewhere else. But what we can do is we can, so if that curve has area 1, we can weight that curve by that when we add it together to make the green one. So in this, if we multiplied, suppose the blue class was 9 times more likely than the red class, then we would multiply that one by 9 and this one leave it the same, and so it would be a lot shorter, and you would get a different shape.
Number 9 is not part of any of these. That's completely different.
That's right. So in many cases, in our simple examples, we'll assume that the classes are equally probable. But I gave an example in week 1 of a medical example where the likelihood is much less. If you look, there have been some discussions about face recognition in the news recently about whether police use of face recognition cameras is appropriate because the false alarm rate is quite high. But that's exactly what you would expect if the people that you're looking for are an extremely small proportion of the population. Every time it flags up somebody, they're 70% chance it's a false alarm, or 90% chance it's a false alarm. But actually, if you think of the total population, you're looking at something like 0.001% of the population are these nasty people that you're looking for. So it does mean that you have to build in careful privacy things about how do you deal with, the distress caused by flagging somebody up as, is that really one of the people that you're looking for? And you need some human intervention there to check that. That's right.
Give a different value, you get a different picture.
Yes, exactly. Yeah. So this is our green curve here that gives us our total probability. So now, applying the Bayes curve to these two, we take this probability of x given omega y, p of omega I, which the red and blue curve, or you can think of it as two curves, one behind the other, we divide by this total probability, and we get this one. So this curve, where we've still got two curves, but the blue curve, you can see on this side, where the red curve is very, very close to 0, p of x given the blue curve and the total probability are almost exactly the same value. So if we divide this by this, which is what the Bayes curve does, we get almost 1. Alternatively, the red is very small. Here it's nearly 0. We divide 0 by some non-zero value here, and we get nearly 0. But as we go through the middle, and we divide, say we're at this crossing point here, we divide the blue curve by this one, the green curve is now about twice as high as the blue curve. So now when we do this division, we're down to about 0.5 here. And then we go down the other side, the blue curve is now around at 0, but the green curve, because it's made up mostly of red, is a very non-zero value, so we're at a 0 value here. And the key point is when there's a crossover point here, that if we want to make a decision based on what's the most probable class given x, we need to do this division, and actually because p of x is the same for both, actually the key thing is which is the biggest product. So is p of x given omega I, p of omega I for the red curve or the blue curve, which one gives this highest product of the model probability multiplied by the prior probability. And that will give us our initial decision. So graphically, this is the sort of thing that we can see is going on as we go through this this probability decision, and this is the decision that we want to make. And in many cases, it's just that's the point that we're going to choose. It's that crossover point that we're going to choose. But we can see that there are some errors that we're going to make around there, and we'll see later how to estimate those errors. So if we now look at how we're going to give a particular example of these, we can start to put some numbers. We're going to make this pattern recognition problem for the character recognition example that we gave. Here, in this case, let's suppose we've got 26 different letters that we want to recognize. We've got these YIs that are our patterns, that measurements that we want to make that come from our sensor. So this is D is 8, so number of dimensions of our space that we're working in. Here we've got a probability of omega j. This is probability of class omega j of being different letters. And here they're not going to be equal. So in English language, for example, the letter E is much more probable than the letter Z. If you've ever played Scrabble, you get a higher number of points by using lower probability letters. If you Morse code, for example, you use longer letters for that. If you've done any sort of coding theory work, you'll know that you can get better transmission rates by using shorter codes for more probable letters. And here's our measurement patterns. Here we're using Y in this particular case. So this is just an example of how we take this idea and this probability of Y given omega j. These are the model probabilities that we would use. Okay, so let's now visualize the types of space that we will work on for our pattern classification things and how this would work out in terms of what those errors look like in terms of individual patterns. So here we think about a two-dimensional space in this example that our patterns might live in. So a couple of slides back we had a one-dimensional line. Here we've got a two-dimensional space. But instead of a probability curve, I'm now thinking of example patterns and where they would fit. And we can see that there's some overlap between the blue squares and the red circles. So mostly the blue squares are over here and the red circles are over here. But we can see there are some regions where there's a confusion between the red circles and the blue squares. And if we wanted to make a pattern decision from here, we'd want to divide this into different regions of the decisions that we're going to make. So one region here, I'm using the Greek letter gamma here, but you can use an R if you prefer. So gamma 1, our region 1 over here, is going to be the ones that we think correspond mostly to the blue squares. Gamma 2, region 2 over here, are the ones that correspond mostly to the red circles. And this shows that there are going to be some of our patterns that will end up on the wrong side, and these are the types of errors that we're going to make. And we'll have to deal with what the cost is of making those sorts of mistakes. And that leads us on to the idea of making the cost of making an error. So given that we've got this probability idea that we've introduced earlier, and we'll have some examples in the tutorials and in the assignment, we need to introduce these decision costs. Here I'm using Greek letter rho, so rho ij, to be associated with, if we've got a class omega I, and that's the real class, but if we associate it by assigning it to class omega j, we need to work out what's the cost of making that assignment. So for example, rho ii, so that's the cost of being in class I, but assigning it to class j, where in this case I is equal to j. What's the cost of making a correct decision? Often we consider that one as zero, so usually we think zero cost for decision. But sometimes you don't have a good choice. Sometimes whatever choice you make has a cost associated with it, and you may want to model all of those costs. There are some things of, there's a game, a sort of mental game called the prisoner's dilemma, where you have two prisoners in different cells, and either they keep quiet or they confess and implicate the other prisoner. And if both keep quiet, then nobody can be convicted, but if one of them confesses, then they get a lenient sentence and the other one gets a strong sentence, this sort of thing. It's one of these, it's actually a non-zero sum game is the idea for this. But you could weigh up what the costs of the decisions could be, and there may be no good outcome for any of these. But the cost of an incorrect decision, this is usually where the cost comes in. If you should have been in class I and you actually made a decision that was class J, then there's a cost of making that mistake. And we assume that the cost of, if you're in class I and you assign to class J, that is greater than or equal to zero, so you don't normally have a negative cost. And you also assume that if you assign it to the correct class, that's a better cost than assigning to an incorrect class. So there are a couple of identities here. As an example of this one, suppose you're automatically verifying a signature on a document or a check that you send to a bank. Class omega 1 is the case that the signature is correct. Class omega 2 is the class that it's forged. If, in this case, you've got two possible incorrect decisions you could make. So one is that it's actually an authentic signature, but you classify it as a forged signature, but the other one is that it's a forged signature, but actually you classify it as an authentic signature. Now, if you really signed a check and sent it to somebody and the bank rejected it, okay, that's annoying, but it's not the end of the world, you can send another check. But if somebody forged your signature and the bank cashed it, this could be very bad because they pretended to be you and they've now got your money. So that means that the cost of a forged signature being classified as authentic is much greater than the cost of an authentic signature being classed as forged. Another way to think about it, your phone might have a thumbprint recognition on it. If it doesn't let you in the first time, you can try again and it'll probably work. That's fine, minor inconvenience. If it lets somebody else in, they've already got your contact information. You might not be happy with that. So that's the same idea from there. So now we can start to ask the question, not just what's the decision cost for one particular item, but what's the decision cost of a particular rule that we're going to make. So let's go back to the example that we had on a previous slide where we've got two regions, region 1 and region 2. We're going to draw a sort of curve between the two that says anything on this side is going to be classed as class 1, anything on that side is going to be classed as class 2. We can now look over that whole space and say, what's the average cost going to happen? So suppose I make this measurement and make the decision lots of times, what's the average cost going to be? And if I'm in a business that has to do this decision many times, this will tell me how much I'm going to have to pay in order to run this system on the average. And so I can do this by averaging out over all the different classes that would happen for a particular measurement X. So at each particular point, I could say, suppose I got this measurement, what's the average cost of making a decision I will make? And this will be the sum up of all of the classes that I could have had. So I don't know if I've seen something from class omega 1 or omega 2. I sum them up and multiply by the probability of omega 1 or omega 2 given that class. And that will give me an average cost at that point. And most likely is that a long way away where we're really clear that it's class omega 1, the probability of being the wrong class is very small, and so this cost is going to be small. Near to the boundary, the probability of the wrong class is almost going to be the same as the probability of the right class. So this average cost is going to be much higher. So this average cost here is just based on the position in that space. And then the total cost for the whole region is to average over the probability of things in that region. So we're integrating over that region. So integral over a set just means that we integrate over the probabilities in that set. And so that gives us the total cost for that region. And then if we want to, we can then add up all the costs over all of the regions, and that will give us the total expected cost for running this pattern classification machine. And so expanding that out, this is just expanding it in terms of the sums and integrals. So it's just made up from the individual costs, the probabilities of the class given the observation times the probabilities of the observation. So this then starts to get us to a point where we can say, right, what we want to do is we want to build a machine that's going to give us the minimum total cost. And so this minimum cost rule says that actually if we want to minimize this value, what I need to do, because these are the same, is I need to minimize this value here. So I need to minimize this sum that the sum over all of the classes of the costs of making, if I was in class I and I put it into class J, given the probability of class I in that space, that's got to be less than if I made some other decision of classifying it into class K. So I'm going to choose at each point the class J as the region that I put things into in order to minimize my cost. And this leads us to the so-called Bayes minimum cost rule. It says, how should I assign X? And it says, I assign X into class omega J if the cost, the average cost of assigning into class J at that point from all of the classes it could have been, because we don't know what the classes were, is the minimum over all the possible assignments that I could have made. Basically, this just says, choose to assign it to the class so that if I came from any of the possible classes that could have happened and given me that observation, the average cost of making that assignment and making the mistake is the least out of all the assignments I could have made. If you like, it's a sort of most protective thing. It's saying, I want to minimize the cost of making these errors. And there's an alternative way of writing this, if you like, using the Bayes theorem, because we don't necessarily have this to hand, but what we do have is the model probabilities, P of X given omega and P of omega. So we don't have P of omega given X, but I can use Bayes theorem to substitute in this. And because P of X is going to be the same on both sides of this equation, then this equation turns into this. It's the minimum cost P of ij of P of X given omega I times P of omega I. And this is an alternative statement for that rule. So just before we take the break, the key simplification that we usually use from here is what are called 0-1 costs. And for these, the probability of assigning to the correct class we think of as being 0. The probability of assigning to any incorrect class we think of as being 1. So this just says, if I make a mistake, it costs me 1 point. If I don't make a mistake, it costs me 0 points. And in this case, this sum from 1 to m over all of the classes of P of ik times P of omega I given x, this is 1 for all of the classes except for the correct class. And because the sum over all classes given x is equal to 1, actually this is the sum over all classes of this, which is this 1, minus the sum for the correct class, where I is equal to k here. So this is 1 minus P of omega k given x. And this leads us to a very convenient way of making a decision, which may seem obvious in hindsight, but it says, for these costs, we assign x to class omega j if P of omega j given x is the maximum of all the possible classes. In other words, for this particular set of costs, we find the most likely posterior probability for each class, and we use the class that has the most likely posterior probability. So that one says, what do I think is the posterior probability of each class, and I'll just pick the biggest, the most likely. That's an obvious rule, but we can see from here where it's come from, that it's come through trying to minimize a cost of making a mistake. And here's a visualization of what this could have been for 3 particular classes of just assigning this. So here are, we've got different values of x along the bottom here, and we've got 3 posterior probabilities that it could have. So the red curve, P of omega 1 given x, is very high over here and goes lower down to that side. The green one, P of omega 2 given x, is low down here, it goes up and increases over here. And the yellow curve is down here and goes up and increases over here. So what region would we assign using this Bayesian maximum a posteriori rule? What region would we assign x to class omega 1? Yeah, so everyone to the left of the crossing point where the red line is the highest, because this is where omega 1 is in this class. How about omega 2? What region will we assign things into omega 2? Yeah, everything to the right of the crossing point here. And how about where we will assign things to omega 3? Never, nowhere, yes. It's never maximum. And this may be a problem for you. If you've got a medical example, this is typically the case that comes up for these rare examples. They never give you the most probable posterior output just because of errors in your test. But that's because we assumed in there that we were using a 0-1 cost for our mistake. Whereas for a medical example, if I go back to the previous slide, this is not very realistic for a medical example, because there is a cost for misdiagnosing somebody might have a disease. They would have to go for an additional check, they would be worried, but hopefully the additional check should confirm they don't have that and they're fine. But if you miss somebody that does have the disease, this is very serious for them, and so there's a very big cost. And that change in cost here, effectively what it does to these curves is it changes the relative weightings of the curves. And so if you can see here in this Bayes rule, it's almost the same as changing the prior probability. In fact, if I go back a couple of slides, you can see from here that we've got the cost, the model probability, and the prior probability. And so if you change the cost or the prior probability, they have a similar effect of increasing the likelihood that you'll choose another class. Okay, so that's where I wanted to get for this point. I'll take a break at this point now and start again at 8 minutes.